Okay, so let us begin. We have a lot to cover. Um, we finished in the first, I don't know, already 4 weeks, I think. We finished basics of machine learning, which was still last time. So we're really starting on deep learning topics as of today. I guess we did a little bit of this last time also. And that was called feed forward networks. Yeah, we did start last time, Monday. And I kind of went over the first two parts of it. And this part, 6.4 of that chapter, is on architecture design for deep learning. And so we hope to cover a little bit of this, which is all the various designs that exist. So we look at a chart of all the various architectures of deep learning that are around right now. It's like almost like a collection of a zoo, a zoo of different kinds of animals, which is deep learning designs that exist. Maybe there are more now. This might be a year or two old, and we'll look at that, and then we'll also talk about the universal approximation theorem. What is this theorem that says that one hidden layer is sufficient to compute any possible function? All right, that's worthwhile looking at. After all, this is deep learning. And isn't there any underlying principles or theory for deep learning? And how would you even go about proving such a theorem? How would you even state the problem properly? How is it mathematically stated, and so on? So we'll take a look at the universal approximation theorem, which says one layer is sufficient, and then we end up with a statement that it might require an infinite number of units to compute any complicated function. That's the downside of having only one layer. And what do you mean by complicated function? Is it has to do some very fine-grained work. An example that we have that I've come across, maybe there are other examples, is to look at a picture of a dog. Apparently, there is a kind of dog. I think it's called a husky. Husky is a kind of a dog which is kind of largely white in color, and to discriminate between a husky and a wolf. And well, what's the complication here? Is they look pretty similar, same kind of ear, same kind of nose, they're white in color, and so on. And it's a very fine-grained difference between the two. And how could you get a program to compute such a very sophisticated function, which is looking at so many pixels and so on? So it's a sophisticated task, but there is a downside to the solution also. They came, a team implemented. Let's do a husky versus wolf design, and they came up with a design for that, and said, what is the accuracy of this neural network for doing this classification? They said it's over 90%. We are very thrilled that over 90%, what a complicated, nice function we have learned. It's able to tell the fine difference between whatever the pointed ear or the nose or whatever it is. It's able to tell that these are two different breeds of dog and wolf, But unfortunately, they found out later on that the program was cheating. The program that was to discriminate between husky and wolf was cheating, because all the wolves were photographed with snow background. They're somewhere in the snowy parts of North America or Europe or something, and they all had snow background. And all the huskies, which are dogs that people keep, they were all photographed with grass and a house and that kind of thing in the background. So the program, instead of trying to learn the difference between the husky and the dog, between the husky and the wolf, it was learning that if it's no background, it must be a wolf, and if it is a home background, it must be a dog. So kind of, anyway, a little bit of a disappointment there on which leads to a totally different topic, which is explainable AI. So you want the program, when it says that's a husky, when it says it's a wolf, you want to ask it the question, why did you say so? If it says something plausible, like the ear was pointed or nose was something, that's an explanation. If it comes out saying, look, the background is snow and the background is grass, then why it's saying so, rather than blindly following what it is saying. It is figuring out something which is irrelevant to the task at hand. Anyway, that's another whole issue. Okay, I don't want to digress too much there. It's a digression, because I was looking for a fine example of what is a very complicated function that a neural network has to learn. And these are the very fine discrimination type of things, which are not easy even for human beings to do. And that would be a complicated function. And so that's where, that's where all this deep learning comes in, because you're trying to do some pretty sophisticated stuff, and a simple design like a logistic regression or a simple neural network or a one-layer neural network will not suffice. Okay, so that's where we are headed. So topics in architecture design. What are the topics we want to go over here? Are basic design of a neural network, some terminology. I found this nice chart of 27 neural network designs. That's not an absolute number. They just collected 27 all over in the literature. And it is nice to get an overview of what all these different models are, just to get an idea of what is the difference between this one, that one, so on. So many of them exist. Just to get a layout of the land before you delve into the particular one that you like. And then specific deep learning architecture, equations for the layers, that's straightforward. And the two theoretical underpinnings, we're all struggling in this deep learning area, instead of simply making it an experimental science. You say, try this, try that. It mostly sounds like that. You said this, said that, oh, that doesn't work. It's mostly practically, you got to do ReLU, you don't need to do sigmoid, all of this kind of stuff, making it very ad hoc. And so we'd love to get some underlying theory saying why should this work. And so these are some of the basic ones: universal approximation theorem that says one layer is enough, and the other one is the famous no free lunch theorem, right? No free lunch theorem says that there is no algorithm that will take a set of samples and learn from them for any arbitrary set of samples that you have not seen. So in a sense, there is no algorithm that can say, whatever be the set you have some set of samples here, and you can say, well, can it generalize to things not seen? There is no program that can look at, any possible combination you can supply that is not seen. It's not going to be there. So there is no such thing as a very general algorithm for any set. So that's something to keep that in mind. All right, advantages of deeper networks and so on. So these are the topics. Okay, here is a intriguing little chart which says what is a basic neural network architecture like. This is not a very standard diagram, but it kind of puts together the most ingredients that go into a neural network or a deep network. And what it is showing here is this is for a supervised learning problem. And this is a supervised learning problem with a regularizer, which is the generalization mechanism. And this says, well, we have a data set xi, yi equal to 1 through n. It's a supervised learning problem. For every xi, there is a output yi. Typically, it's a scalar value rather than a vector value. And it could also be vector if it is kind of giving ratings for all the possible classes. And we have an input x then. One of the samples x could be fed in, and then there is a network with a set of parameters w, which could be several layers, which could consist of w1, w2, etc. Set of weights corresponding to one layer, set of weights corresponding to next layer. So all together we refer to a set of weights. So to given an input x, given a set of weights, this thing computes some function f of xi w. Xi is the input coming here, and w is the set of parameters here. It computes some function over here. So any given set of weights is going to compute some function, but we want to see how good a function it is. So we can measure the loss L sub I, which is the loss associated with the ith sample. And the total loss then is the loss associated with the ith sample. And when you say loss, it's a function of what is being computed by the function, as well as what is the correct output vis a vis. So it is taking the two and computing the loss. If they're mismatched, it will have a high loss. If it is exactly the same, the loss would be 0. So that's what's happening here. And we're looking at the total loss function here. And then what else is happening here? So that is the loss. And then this W also is fed to a regularizer R. That kind of also gets added to this loss here. And we call it as a regularized loss, which is the loss L. R or W, we can denote it as L tilde. So there is a regularization that's going on. So this is the structure, and the objective of learning would be to minimize this loss function and do backward propagation to go and fix the W's over here through all the layers so that the loss is minimized. So the way we do it is using gradient descent or stochastic gradient descent. So this kind of gives you a picture of what is happening in any neural network or a deep learning network. Of course, the kind of regularization sometimes we use may not be of this form. This is called a norm penalty, where the regularizer is using 1/2 W squared. That is the length of the vector, length of all these vectors here is what is being used over here. So that is one type of regularization, and there are dozens of others, which is also a topic we're going to look at. But this just is showing the classic norm penalty. And this is something to keep in mind, is what is going on in a neural network or a deep learning network. And of course, we have seen simpler versions of it. And if you had a simple version with only one hidden layer, and this is explicitly showing all the weights, how they're used here, and explicitly the biases are represented. So basically, this is the simplest version. First layer is given by this, and then second layer is given by that. So these are the activation functions, G1 and G2. W transpose X plus B, that's the bias here. W transpose X plus B, that's the bias there. So this gives you the hidden layer at the first level, and then second layer is hidden level. So this is the kind of thing that's going on here. And all of this can be shown as matrix multiplication, W times X plus B. B, of course, sometimes we get rid of it by choosing one more input with a value 1, and so we can get rid of that by some kind of a normalization. So anyway, that's the design with the 2 layers. So we talked about the general neural network and what a 2-layer network can be. So then the question is, the word architecture refers to the overall structure of the network. How many units should it have? How the units are connected to each other. I suppose we should also talk about what kind of units there are. That's missing over here. Saying what kind of unit, because some of the units are of different form, as we will see in the next few slides in the compendium of different networks, and they are organized in terms of layers. It's all the basic stuff. And deeper networks have far fewer units in each layer, far fewer parameters, often generalize well to test set, and are often more difficult to optimize. All right, because you have to propagate the gradient. Why are they difficult to optimize? Is you can have saturation and nothing is changing, and so there is a whole issue of the vanishing gradient issue and so on. So those are some of the things that need to be dealt with. So anyway, we'll talk about choice of depth and width. I like this particular chart. All right, I found it somewhere online. I think there is a reference to that. So this person collected all the different architectures. It's worth looking at all of these to see what all there is, and you can pick and choose which architecture you like. You know, the basic perceptron is where things started, where it is basically taking the features and finding some weights to multiply the features with, and you add them up, compare it to a threshold to see is it yes or no. It's a 2-class problem. Perceptron does that. It could be generalized to multi-class by having a softmax function. Feed forward is a general network where we have inputs, we have hidden layer, and an output. And then this looks like radial basis function is almost the same kind of thing, where we are specifically choosing the Gaussian type of kernel type of thing that we input everything to. And a general deep feed forward network would have several hidden layers and then output layer. And then there are all these other specialized ones, RNN, referent neural network. There's some kind of feedback loop going on here. And this one explains, I guess, it just shows the the loop here, and then we have several layers like this, and an RNN would have this kind of a structure. Long short-term memory has this structure, which reminds me, project number 2 has been put online, right? You might have seen it on Piazza. You finished project 1 on Monday. Project 2 is out there, which is simple convolutional neural network for the fashion MNIST data set, another classic data set. And I've asked the TAs to make some variation, so it's not a standard one you already know the answers for and all that. So some small variations so you can appreciate what's going on. So that's project number 2. Project number 3, which is what reminded me of this. We are still working on project number 3 description. When you finish project 2, so the due date for project number 2, and in another, so that is going to be one on this stuff, recurrent neural network and long short-term memory. We haven't really finalized. It's going to be on sentiment analysis. If you are given a bunch of movie reviews and you have said this is a positive review, this is a negative review, that kind of a thing, and can you take a review in the future and say, is that a positive review or a negative review? Simple task. Only thing is you have to process language part. We're trying to make sure that it's not too complicated on the pre-processing of the language part of it. And we'll be using embeddings and things like that. So that's why we have to be careful to make it something that we can manage to do reasonably well on sentiment analysis. And the fourth and the last project, which will probably be the next slide, is going to be on the generative adversarial network, and using some variation called the self-attention. Yeah. Okay. So anyway, these are all the models. I think this tries to explain how these are all. And here is, for example, autoencoder, which autoencoder simply reproduces at the output exactly what was input. So it's like a very strange network whose job is to take an input and produce the same thing as the output. Only requirement here is it can't directly produce them. It has to go through a constraint here that you got to encode it with as few units as possible and capture what is the essence of this computation or whatever it is you have, to bring it down to essential parts of it. The essential parts should be used again to reconstruct the origin. And how good this constraint is being handled by the autoencoder. Of course, if you have more and more of those units, it's going to do better and better. But you want to get an essential representation. Basically, it is learning some features over here. Auto means the same thing, autoencoder. Right? And there's a variation of it called variational autoencoder, which is a pretty powerful thing. And this one has units that look strange, which are probabilistic hidden cells. And you bring in interesting ideas here. How do you have a probabilistic cell in a neural network? And we use a trick, just like the kernel trick in SVM. We use another trick here, how to replace the probabilistic ones by using N01 and so on. So it's a very interesting architecture. Variational, because KL divergence comes into play here also. Denoising mode. I don't know all these architectures myself, but it's kind of interesting to see what all exists over here. There is a Markov. Okay, that's a very standard probabilistic graphical model. Markov chain is simply a set of variables connected to each other that represents a probability distribution actually. And Hopfield network is some variant here again. And this is something called a backfed input cell, whatever that is. Boltzmann machine is interesting. There are inputs and outputs, and it's a probabilistic model. And a variant of it is called a restricted Boltzmann machine. Those become generative models. So all those things on top are all generative models. What it is they are capturing a probability distribution. So you have presented a data set, and we want to say what is the distribution. Keep in mind that machine learning, deep learning, what is it they are doing? You present them data, and it's figuring out what is the distribution of data in some way or the other. And using as small a set of parameters to represent it as possible. So now it becomes a generative model in the sense, you captured the distribution, so give me a sample from your distribution. So in that sense, it becomes a generative model. slightly different kind of thinking than the classic supervised learning problem, input to output. Well, isn't it just a box that matches the input output behavior? That's called a discriminative model. So it is saying which one is it? So the discriminative model, as opposed to a generative model, which is simply capturing the distribution, and it could be a conditional distribution, or it could be a joint distribution of the input outputs and the things. And you can always use a generative model to do the task of discriminating. So because once you if you know the joint distribution of p, x, and y, you can always generate p y given x from by simply marginalizing it and using Bayes rule. You can always compute the generative solution, discriminative solution from a generative. Deep convolutional network, deep convolution. Okay, some more of these things. Very nice pictures. Here is generative adversarial network. Okay, so how does that fit in here? We'll be looking at that. You're going to be doing a project on that. Liquid state machine, extreme learning machine, eco state network, deep residual network. Okay, this I think is a very popular one nowadays. Residual network, ResNet they call it. And then neuronal network, support vector machine, neural Turing machine. Aha. So if you are a theoretical computer science person, you might enjoy looking at those kinds of things. Anyway, that's just an overview. And every one of them has all kinds of sophisticated discussions. There could be a whole lecture and chapter on all of these topics. Of course, the big workhorse of all of this is the CNN convolutional neural network architecture, which goes through convolutional layers, subsampling layers, convolutional layers, subsampling layers, a fully connected network. And all it is doing is telling you what is the 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 handwritten digit recognition. And as I said, handwritten digits have been the fruit fly of AI to try out to see how well it does on that problem. The terminology has changed a bit. Subsampling is now referred to as spooling, and then convolution where you're patching a kernel. And you have feature maps that are obtained by having kernels of different size and so on. And, okay, so we'll get into CNNs to see how all these different layers in CNN are. And anyway, at every layer, it's learning some features, put them together to do some feature like classification type of problem. So this is what you're going to be implementing in project number 2. And I just started getting pictures of all kinds of networks. I threw a few more in here. Some of you, I think, would be interested in deep reinforcement learning. And what does deep reinforcement learning look like? It is really just sensory processing. If you got some video, images, things like that, a game playing program, and all of that is sensory processing is going on here. And then this is a very standard environmental feedback thing with a reinforcement learning type of setup. And so it's some combination where the sensory stuff is all being done by standard deep learning. And then there's something called Q learning that goes on in reinforcement learning, where you have the environment providing feedback when you do something. What is the kind of feedback you're getting? So it remembers those. And so, but those are all connected up to a deep learning network. So it's an interesting subtopic about combining deep learning with reinforcement learning. Okay, anyway, so there was a whole bunch of these architectures you can look at, and you can look at and decide which ones of these are interesting to you. And all of them provide a very rich area for doing any kind of theoretical work. So the theoretical work, theoretical underpinnings, mathematical theory of artificial neural networks, linear, nonlinear models, universal approximation theorem, no free lunch theorem, size of the network. These are some of the theoretical issues. So these next few slides here try and cover that ground. And a linear model, matrix multiplication only represents linear functions. So we just don't want a simple function with no nonlinearity. And so we need nonlinear functions, which are like sigmoid or ReLU, things like that come into play. So we talk about linear, nonlinear. Then, of course, we move to this theorem that says as long as you have any kind of nonlinear function in there, A feed-forward network with a single hidden layer containing a finite number of neurons can approximate continuous functions on compact subsets of Rn under mild assumptions of activation function. Okay. So it says you can compute any function. The problem of huskies versus wolves. Okay, maybe there's a. I would like to look at another fine example that a neural network can do. Maybe you can find one and show me. It should not. The handwritten digit 0, 1 through 9 is a relatively easy problem, and one can get 99 point whatever % accuracy. But there must be some very, very sophisticated fine-tuning thing that even human beings can find it difficult to tell them apart, and a neural network can learn to do that. So then we say it's computing a pretty complicated function here. All right, so we can compute any complicated. That's what we mean by a complicated function. Simple neural networks can represent a wide variety of interesting functions when given appropriate parameters. However, it doesn't touch upon algorithmic learnability of these parameters. Okay, so there are some issues. They can represent, but will the algorithms do that? Yeah. Yeah. You know, this is the thing. Okay, maybe this kind of goes on to talk about what is a mild assumption. Non-constant, bounded, monotonic, increasing function. These are the kinds of assumptions that we need for that activation function, which is written up here as C is that function. So the mathematics of it gets pretty hairy here. We're talking Borel functions, sigma algebra, pretty sophisticated math here. But it's worthwhile to get a sense for how this is stated even, right? This slide is the one that tells you how would you go about saying one layer is enough. This slide tells you that. So we have an activation function P, continuous, non-constant, bounded, monotonic function. This is for continuous. ReLU is not continuous, but this is stated in this way. IM is the unit hypercube 0, 1 through M. It says there are M inputs and every input is binary. So it is stated for that problem. You can always generalize it to non-binary, multi-valued. They're just taking. Let's take this problem where I give you a vector of zeros and ones. That's the input. And space of continuous. So we have some continuous function on IM. So it's a function. That input is mapped to something. Is CIM continuous function is this. Then given any function f belongs to this. So any function that takes this black and white, I suppose 1 and 0 is a black and white image. It's trying to say that black and white image is of Mahatma Gandhi or whatever, right? Famous person. And then given any function f and epsilon greater than 0, there exists an integer n, number of hidden units. Real constants vi, bi, output weights, output bias, input bias. Real vectors wi, input weights, such that we may define, all right, this neural network defines, it's computing some function x. This x is coming from a list of zeros and ones. Summation vi phi of wix plus vi. That's the standard neural network formulation. You're multiplying the vector, there's a bias here, we're computing the activation. We are summing over as an approximation of f, some complicated function that is mapping the 0, 1 image into, that is Mahatma Gandhi. That's something, right? A black and white image. That's why I'm using an old photograph. And so this is what the algorithm is doing, neural network is doing. F is the real function, small f is the real function. Difference between this function and this function is less than epsilon for all x. That is, functions of the form f of x are dense in CIM. So this is saying that is needed to say that neural network, some neural network, can actually do the job. This complicated function can be computed. That is how the universal approximation theorem, since it's a theorem, there's got to be a proof for it, which gets a pretty hairy stuff. And because it says, implication of universal approximation theorem. A feed-forward network with a linear output layer and at least one hidden layer with any activation function can approximate any Borel measurable function from one finite dimensional space to another. What the heck is a Borel measurable function? If x to y is continuous mapping of x, where y is any topological space, xp is a measurable space, and f inverse of v belong to B for every open set V in V, then f is a Borel measurable. All right, the mathematical experts tell us that that is the way. You gotta get Borel type of stuff. So anyway, not super mathematicians here. Maybe some of you are, and that's what you would have to go through to show the UA theorem or the universal approximation. Practically speaking, it is saying one layer is enough to compute any computation, provided network is given enough hidden units. The derivatives of the network can also approximate derivatives of the function val. That's important because you need to learn, and this network will have to deal with derivatives because you're going to be changing the weights. Right. So applicability of the theorem is that any continuous function in a closed bounded subset of Rn is Borel measurable. So that is about functions, and this case is a neural network may also approximate any function mapping from any finite dimension to another. Original theorem stated for activations that saturate for very negative positive arguments. There's the issue about the activations. What is the nature of the activation function? The sigmoid is a saturation type of thing. It kind of goes from always all 0 and then makes a flip into 1 and then always 1. It saturates over there, which is kind of a disadvantage of the sigmoid. It's a differentiable function. That's why we choose the continuous rather than a step function. There's a derivative there. Problem is it saturates, which is what also true for wider class including ReLU, which is not continuous. And ReLU has this advantage that it doesn't saturate, it goes, it's a line along 0 and then suddenly it goes to 0. And that is its power. And we already work on deep learning, some of the work done by Jeff Newton. There is a particular slide somewhere I heard. One of the students, Alex, he wrote a paper about 10 years ago. And that network is called Alexnet. It's a nice paper. The student's first name is the name of the network. And he showed that if he sigmoid type of thing, the amount of epochs and all that is taken is so much larger than using ReLU. And that was kind of a revelation that that this saturation problem is solved. Otherwise, they would not have been able to train the network. The particular problem they were attempting was, I think, a competition where they had complicated images of ships and dogs and cats and trains and cars and whatnot, very realistic looking images. And there were 1,000 classes saying it can be any of these. There are container ships. Okay, that's one class. So on these realistic images, they needed to do that classification on this complicated real looking images. And they won the competition by implementing this network with ReLU units. And in that particular paper, when they wrote it up, they said, well, if we had used sigmoids, this would not have been feasible at all. And so they had to move to ReLU to do something as complicated as that. There is all kinds of other discussions. Why does ReLU work? What about the point of discontinuity and so on? But the advantages you're getting are the linearity and non-saturation type of thing. All right. So theorem and training. Okay, whatever function we're trying to learn, a large multi-layer perceptron. MLP is multi-layer perceptron, not machine learning. Multi-layer perceptron will be able to represent it. However, we are not guaranteed that the training algorithm will learn this function. So optimizing algorithm may not find the parameters, may choose a wrong function due to overfitting. So it doesn't mean a particular architecture will actually find it. The theorem is a general statement. And so you will need to find the right number of parameters. The particular optimizing algorithm you're using, like stochastic gradient descent, may not find the parameters, may choose a wrong function due to overfitting. So the no free lunch theorem says there is no universal procedure for examining a training set of samples and choosing a function that will generalize to points not in the training set. That's a more formal statement. It's also a theorem, so it would be interesting to see how do you prove the no free lunch theorem, right? Okay. So feed forward and no free lunch. Feed forward networks provide a universal system for representing functions. All right, we say it's a system for representing functions. Given a function, there's a feed forward network that approximates that function, however complicated it might be, right? Huskies, that's the one current example, running example I have. Huskies versus wolves is a complicated function. It can learn that, whatever be the fine variation between the two. There is no universal procedure for examining a training set of specific examples and choosing a function that will generalize to points not in the training set, right? So these are the two things that are being said about to keep in mind in perspective. Okay, then there is something on, there's an interesting issues about size of the network. Universal approximation theorem says there is a network large enough to achieve any degree of accuracy, but does not say how large the network will be. Bounds on the size of a single network exist for a broad class of functions. And so anyway, there are some formal statements about this. So we already seen what the universal approximation theorem. This is the example I found, which was on huskies versus wolves, right? The ones in this kind of a brownish color are all huskies, and the ones with the yellow are the wolves. And the program did 90% accuracy, but then they found all the wolves have snow background. So it was just saying, as if you have snow background, it's got to be a wolf, and if it has got a green background like this one or a green background like this one, it's got to be a dog. That's a dog there. All right, and this one, I suppose, it had a peculiar background. It didn't know what to make of it. So, anyway, a difficult example. I was just looking for an example of a difficult function to learn, but this one, the program did not really learn the difficult function, but it cheated and looked at something that made the problem solvable without really learning what it took. These are all you can find it in blogs on why should there be explainable AI. Right? Why is explainable AI needed? And they went on to talk about, well, that is just a fun example, dogs versus huskies. But they give some realistic examples of medical situation of pneumonia and asthma. All right, how in a medical situation, the program had to figure out what is a serious case and what is not a serious case, and it kind of peculiarly went about saying if a person had pneumonia and then got asthma, then they were less at risk, which was actually the wrong thing it was learning. It had missed the fact that people with pneumonia would have been treated already, and so under care already. So they were less at risk because of that, but it was missing that point. So anyway, all of this comes into explainable AI. If that's a topic of interest to you, as to how would you explain? How do you get the program to tell why did you say this is a dog? And maybe you will catch it when it says, that's because there's a white background. So then you will know that it was doing something like that, right? That's this is the slide I've mentioned already about Alexnet. So they had all these input images and convolutional neural network layers and a fully connected layer, and this is the kinds of tasks they had, 1,000 labels. This is saying, mushroom, cherry, Madagascar cat, leopard, motor scooter, container ship. So these are the kind of things, classes that it was dealing with, 1,000 classes like this. And this is the chart they had. If they use the hyperbolic tangent, this is the number of epochs, the number of times you're presenting the samples to the network to modify itself. And this is reaching the 25% error rate. The number of epochs needed, the tanh would keep on going like that, whereas with the ReLU, it was approaching it quickly. And the conclusion, this is in that paper. It's a very worthwhile paper to look at. That's Alex and Jeffrey Hinton's paper, 2012, an 8-year-old paper. It very nicely delineates, because they were kind of the first ones to explore this ReLU idea and say that was needed for us to win this competition. It would not have been possible if we were using tanh. Tanh is just a variant of sigmoid. right? There is a simple relationship between the tan h function, 1 over 1 plus e to the minus x, something like that. It is kind of related to the sigmoid function. So that those all saturate, and ReLU does not saturate. And so the point they made is deep CNNs with ReLU is trained several times faster than the equivalents with tan h units. ReLU reaches 25% error rate 6 times faster than with tan h neurons. Not possible to experiment with large neural networks using traditional saturating neuron models, right? I mean, for a long time, neural networks have been around for 50 years or more. Myself, I've been teaching it for 40 years, and we always used to drill into students the idea that, oh, the reason we're using sigmoid is because it's differentiable and we need to do derivatives, we need to do backpropagation and so on. And suddenly we are saying, no, it doesn't have to be. So we can bring in another variant called ReLU, and that is absolutely necessary. So, you know, you see in the literature, they're saying there is a place for sigmoid and ReLU. All right, it's not like one is completely replaced the other. All right, so you know, under what conditions and all becomes an interesting question. I think there is some nice guideline. Even in my slides, I think you'll find it somewhere. All right. So anyway, for large networks, ReLU, right? Large networks like this. Okay. Depth. There's some interesting discussion here and some theorems on depth. How the number of linear regions carved out by deep rectifier network with the inputs is this, and so on. So there are some theorems on depth and statistical justification of depth. And okay, what is it? So there is some math behind it. The main point in looking at some of these things is some of you may come in and saying, what is this kind of ad hoc experimental science you're talking about? Where is the real science behind it, right? And so there is stuff like this to help us understand these networks, and it's a nice domain to look at. A deep architecture expresses a belief that the function we want to learn is a computer program consisting of m steps. Yeah, that's the analogous to it. So you have some problem, you're trying to write code for it. Then you ask, how many lines of code do I need? Right? Somebody writes it with 3 lines of code, the other somebody else writes it with 10 lines of code. Which program is better? So one you can say that is 10 lines is like a depth of 10, depth of 3. There's no right way, and but the deep architecture expresses the belief the function we want to learn as m steps, where each step uses previous step's output, and intermediate outputs are not necessarily factors of variation, and they're analogous to counters and pointers. And empirically, greater depth results in better generalization. Factors of variation is a very interesting concept. So when you have like a face or whatever, what are the factors of variation of the faces? Factors of variation, for example, the pose, right? Is it a frontal or it's a side, and whatever we refer to that. So the input can be varying, and one factor may be the pose, another factor may be the lighting or illumination, or it could be I don't know, the camera angle and so on. There are so many factors of variations that's affected. It would be nice if somehow the program is learning the factors of variation, that it is saying this is a face in this particular orientation and so on. If it captures that, it would be nice to have that in our explainability here. But in a deep learning network, they're not necessarily finding the factors of variation, but it's computing something along intermediate ways. Other empirical results: deeper networks perform better. Test accuracy consistently increases with depth. So this is the depth is being used. Test accuracy was going from 92.5 to 96.5%. So a depth of going to 10 layers is doing better than 3 layers and so on. And increasing parameters without increasing depth is not as effective. What about simply using a large number of units as parameters? Free parameters, some convolutional network, fully connected, so on. Test accuracy, what happens? The number of parameters increases. Sometimes it goes down here, and for different of these models. So deep architectures indeed express a useful prior over the space of functions the model learns. It's a prior. kind of intuition that having multiple layers does better, and you are kind of building that knowledge into it explicitly, saying that's the prior that I'm giving it, and that the prior is saying the prior is depth helps, right? Of course, it gets more complicated. You run into issues of vanishing gradient and all kinds of issues like that come up, also practical issues. So there's some trade-off. All right. Let me just mention the next topic within only 5 minutes. Aditya is waiting outside, reminding me that he needs to take over shortly. All right. So the other topic I wanted to cover was this is a very interesting section called computational graphs. So this is about the use of these graphs in deep learning is pervasive, so you would have a good idea of what these computational graphs are. Computational graphs are different from probabilistic graphical models, for instance. Right? So here the nodes of the graph correspond to variables or operations. Very intuitive actually, but specifically we need to know how these things are. And I made a collection of things. One was a computational graph way to illustrate what happens when backpropagation is being used to compute derivatives. It's an interesting sequence here. I can't just go over all of this very quickly, but you may want to look through it. Saying, supposing I have a function f of x, y, z equal to x plus y times z, and a specific example, x equal to minus 2, y equal to 5, z equal to minus 4. And what is that computation? And we can say, well, it consists of q equal to x plus y and f equal to qz or qz. And then we can say, if we wanted to compute the derivative of that, so there is a forward computation that's going on, and we are interested in computing the derivative. That's what we do in backpropagation. So it kind of illustrates how these computations can flow in a computational graph. And another interesting thing comes out of it is you're computing the derivative at a particular point of that function. Right? So for instance, x equal to minus 2, 5, 4 of that computation here, q becomes equal to 3 when x equal to minus 2 and 5. Adding the 2, you get 3. And then the f is equal to q times z, which is minus 4, which is equal to minus 12. That's the computation that's gone on. But what we are doing over here is also to show in this computational graph, supposing I say, what is the value of the derivative at that point x, y, z? And how would you compute the derivative of the function f with respect to partial derivatives, with respect to x, with respect to y, with respect to z, because that is what is needed. The vector of partial derivatives are needed to update the weight vector. So this kind of this series here, it tells you we are interested in first delta f by the derivative with respect to f itself, which is equal to 1 here, and how we backpropagate the derivatives and also invoke the chain rule. How we go about, we need 3 values: derivative of f with respect to f, derivative of f with respect to y, and with respect to z. So derivative f with respect to x is also derivative f with respect to q, and then derivative q. This is the chain rule of calculus, and how these values in this computational graph are computed. And also we need to look at the chain rule applied to a simple neuron here. So these are the main components, but more generally, a computational graphs are a nice way to think about math expressions. Consider the expression E equal to A plus B times B plus 1. It has 2 adds, 1 multiply, and they introduce a variable for the result of each operation. So this would become a computational graph for that expression, that we have C equal to A plus B, and then we have D equal to B plus 1, and D equal to C times D. So that's a computational graph. Such graphs are useful in computer science generally, especially functional programs. And then core abstraction and deep learning using Theano. Theano is kind of an older version of PyTorch and TensorFlow and all that. So to make a computational graph, operations and inputs are nodes. So these are inputs A, B. Operation is A plus B or B plus 1 are nodes, and values used in operations are directed edges. So the values used, let's see if that is illustrated in the next slide here. Okay. So I guess we take values here, set the input variables to values and compute nodes up through the graph. We have A equal to 2 and B equal to 1. So we have C equal to 3, so that these things move up here. And this simply illustrates that computation. Seems like a fairly obvious thing. Expression evaluates to 6. And we, you may want to keep in mind where is this going to be used, even at the level of backprop or more generally. So computational graph language. To describe backprop more precisely, computational graphs is useful. Each node is a variable or an operation. And it is a more interesting example of a computational graph. We are saying this operation is x to the power of 2, and this is v equal to h of x, and u equal to g of v. This is equal to f of u, and it's a composite function. F equal to h of x, f is f of g of h of x. So this is f here, and that's a function of the argument is g, and for that the argument is h, and that's what's being f of g of h of x. And what if f was e to the power of x, and g was sine of x, and h was x squared? So we say f of g of h of x is e to the power of g of h of x. So that is what is being computed with all of these substituted in. What is g is sine of x, h is x squared, and so on. So every connection is an input, every node is a function or operation. So we end up finding this to be useful because we're talking about function of a function of a function. That's what a deep learning network is doing. This is the nature of a deep learning network's computation. So which is why this kind of formalization becomes a useful thing, right? Chain rules. And then we all normally talk about computing derivatives. There we talked about a simple function, and now we're talking about what about derivative of this? All right, so how do we compute derivative here? And again, we invoke chain rule and so on. This has worked it out completely of what the derivatives look like. All right, derivatives. Okay, so the reason I gave that simple one earlier on was this gets looking very complicated now. But it's kind of interesting to look through this whole terminology of, and then there is also how do we save on computations, because a lot of things are happening at the different pathways and so on, factoring the paths and forward and reverse mode differentiation. Pretty much a lot of stuff here, all right? I found this stuff on various, Kola is some youngster like you all. I like his blogs. He's trying to explain all these complicated things, and he made up all these examples, and I found it useful. Okay, all right. I'm going to stop here because Aditya is waving to me. Aditya, are you here? Okay, there he is. Okay, all right then. So he has made up a quiz. You know what happened? The first quiz that I gave, that I gave to you, I had given it last semester, in the US. And then I gave it to Aditya and all, saying, give the same question. Just, sir, this looks too easy for our students. These students all were in the top 100 in the GATE exam. They'll find it too simple. So, okay, I got to raise my standards in India at IISc compared to, where I teach. So, okay, you make up questions then if mine is too easy. And they made up so hard questions, I couldn't answer them myself, right? Eigenvalue and eigenvector and all these things they put in. So I kind of had to negotiate saying, okay, don't make it too hard, make it useful, make it at your level. And but then the second quiz, we are going with whatever we had, right? Okay, I finally got vindicated that I wasn't teaching it in a too low a level. So the quiz you're getting today is the same quiz, right? With some improvement in the wording. Some of the wording was not good. So you're getting the same quiz I gave last semester. And I had the same issue. My TAs were smarter than me there also. Here also my TS are smarter than me. They're saying you are giving too easy. Anyway, we negotiated that. Let's see how you all do on this quiz. It's basics of machine learning. All right, take over, Aditya.